I'd like to now talk about non-standard cells. Up to now we've been talking about standard cells where the concentrations were 1 mole or 1 atmosphere, pressures were 1 atmosphere, etc., etc. But now we can actually calculate the cell potential of non-standard cells if we have the Nernst equation. And the Nernst equation is this one here. E cell equals E naught cell minus 0.0592 volts divided by N times log of Q. And Q is our friend, the reaction quotient that we've been dealing with up to this point anyway. And I'll show you how we can calculate the cell potential using the Nernst equation now. Here's an example. Notice that in the example we've got everything set up the same way, except that we now have concentrations for the non-standard portions of the cell. So Cu2 plus is 0.50 molar, this is 1.00 molar, this is 0.50 molar, and this is 2.00 molar. Notice that the solids don't have any concentration associated with them, and that's because they're solids. So we're looking for E cell. Notice it's not E naught cell because it's not a standard cell. So E cell is what we're looking for in this case. So what do? Well, we first of all look at our reaction. This will be our anode, and we know that this will be the oxidation. So I'm going to go hunt down that reaction off my electrode potential table. And we're looking for something that involves copper and copper 2 plus, and there it is, copper and copper 2 plus. And this is 0.340 volts, and since it's the anode, it's oxidation, so we're going to flip that. We flip the reaction, we flip the sign, it becomes negative 0.340. You can see what we've done here. Remember, everything on this table would be a reduction, and since we want an oxidation, we have to flip the reaction. Alright, so we do that. Now we're going to hunt down a reaction that involves Mn2+, MnO4- and H3O+. Okay, so where is that one? Alright, there it is. We've got MnO4- here. We've got H3O+, which is really H+ in this case. Then we've got Mn2+. And again, we have to make sure that we've got exactly the same species. See, we've got our Mn2+, we've got our MnO4-, we've got our H3O+, so everything matches. Because there are some similar ones in there, like you got this MnO2 and Mn2+. Just got to make sure you don't grab the wrong one. Alright, so that's 1.51 volts, and we don't change that reaction because it's supposed to be a reduction anyway. Now we've got 2 electrons up here and 5 electrons down here, so we need to do something to make these electrons equal. So what we do is we multiply this one by 5, we'll multiply this one by 2, that will give us a net amount of 10 electrons in each of these reactions. Alright, so we go ahead and we add those reactions together. This is what we get. And you'll notice I've got the 5 in front of the copper, I've got 5 in front of the copper 2 plus down here, I've got 2 in front of the permanganate, 16 in front of the H plus, 2 in front of the Mn2 plus, and 8 in front of the H2O, that's 2 times 4. So I've just gone ahead and kind of done the multiplication out here. Everything that was on each side of the arrow remains on that side of the arrow. So the copper 2 plus is still here, the Mn2 plus is still here, and the H2O is still here. And everything on this side is still here as well. So a good tip is to try and maybe keep the arrows aligned. That way you won't get confused with what materials are on each side. Along with that, I go ahead and I add those together, and I get my E naught cell value. So this is for the standard cell right here, and that's what we're working with. The E naught cell is still part of the equation that we need. See, E naught cell is here in the Nernst equation, so we will be making use of that. My next mission, though, is to find Q. Now, Q is found pretty much the same way as it's been found in the past. We take our products over the reactants. Now we ignore water and we ignore solids, and again, solids are ignored because they don't have any concentration in the solution. So another tip you can use is just look at the initial equation or problem that you're given, and you'll see anything that's got a concentration next to it, you better be finding that somewhere in the Q expression. So that's a good idea to kind of check it against that at the end. Alright, so we've got our Q. We know it's Cu2 plus to the fifth. It's products over reactants. Cu2 plus to the fifth, Mn2 plus to the power of 2. On the other side, we've got MnO4 minus squared, and we've got H plus to the power of 16. So all of that is down there as well. So now what I do is I just sub in the values, and the values come from the initial question. So I just sub those values in. I get a value of 1.9 times 10 to the negative 6 for Q. Now I can go ahead and substitute in all my values. I found E naught cell. I've got 0.0592 volts divided by N. Now N is going to be the number of electrons transferred in the balanced equation. And you'll see that to get to this balanced equation, I had to multiply this by 5 to get 10 electrons, multiply this by 2 to get 10 electrons. So the number of electrons that was transferred was 10 electrons. So N is 10, and then it's log of the Q value I calculated, 1.9 times 10 to the negative 6. I do all that calculation, I end up with 1.20 volts. You'll find that these non-standard cells usually don't vary that much from the standard cells. This was 1.17 volts for the standard, and this only went up by 0.03 volts when we changed the concentrations the way we did. Alright, while I've got you here, let me give you a summary of what the signs and magnitudes of values indicate. If we look at delta G naught, delta G naught is less than 0, that's a spontaneous process. E naught cell greater than 0, that's also spontaneous. When K is greater than 1, what we're saying is that there's more products than reactants, so we're looking at that as being spontaneous as well. Non-spontaneous processes, delta G is positive. K is between 0 and 1, and E naught cell is negative. So those are all good to know so that you can make sure that your answers are correct and they're what you expect them to be.